respected Sri D.S. Chaskar sir, Ankit ji and esteemed participants, very good morning to all of you. Although we are at the end of the second week, but I once again welcome you in this course. As we have told earlier during the inaugural webinar that in addition to the inaugural and concluding webinar, we will have some more webinars in between to discuss the issues which are being faced by the participants. So this webinar is for the enhancing the knowledge of the participants and clearing the doubts and problems what they are facing in week 1 and week 2. For this webinar, we are having the faculty Shri Ankit ji. Ankit ji is a expert in hydrology. He's executive engineer in Central Water Commission. But before starting the webinar, I want to mention some issues here. Many of the participants have not yet started the course. Even the 2 weeks are completed now. But they have not started the course, or even they have not logged in since last 10 days, more than 10 days. So I want to say that even in the starting, I have told that for this program, we received an overwhelming response, and your nomination was included in the cost of others. So please, please join the course. Please go through the materials and attempt the quiz, submit the quiz. So then only this program will be beneficial for you. And even if you want to attempt the quiz later on, if you are thinking that, so you will get to know that your work will be piled up and you will not be able to complete all the quizzes in 1 or 2 weeks. So in addition to this, I am seeing that many of the participants have attempted the discharge calculation, but still they have kept it in the draft position. So until unless you will not submit it, we will not grade it. So please submit it, and then only we can evaluate. So we will have the webinar, but before that, I will request Shri D.S. Chaskar sir to say the few words to the participants. Sir, over to you, sir.
Thank you, Ashit ji, and very good morning to all. Good morning, Ankit. It's really nice to see you joining for this webinar as a faculty. Friends, we started this distance learning program almost 2 weeks back, and the modules of 2 weeks have been taken by many participants. And as told by Ashit ji, there are few participants who are yet to clear the modules. They have yet to pass the assessment which is given for every module. So my request to all of you would be to follow the schedule that is given for this training program. There are modules for every week. There are certain activities for every week, like giving the feedback, submitting the assignment. So these activities are required to be completed by you in that week itself. And let me tell you once again that this course is kind of a faculty assisted self-study course. Okay, unlike other training programs where everything is delivered to you through presentation, online presentations, here we have very good modules which you are supposed to undergo, you are supposed to read on yourself. Okay, then based on the reading you have to take the assessment. In the assessment you should get 70% marks. Okay, and we will be able to give you certificate only if you complete all the given assessments with 70% marks, as well as the assignments which are there. Okay, so my request to all of you would be to please follow the schedule. Please tell your colleague who is also there in this program as a participant to remain up to date. We are reaching out to the participants who are lagging behind in the schedule, and we will be soon contacting them, because as I said, just participating in this presentation or in this program is not sufficient. Okay, to get the certificate, which is internationally recognized certificate signed by National Water Academy and also the officers of World Meteorological Organization, you need to complete the activities with certain grades, that is 70% and more. Okay, and every activity is compulsory. So uh, my request to all of you again would be to follow the schedule. In the last 2 weeks, very important modules were covered. uh, the first module, which was supposed to be undertaken as a part of the pre-course activity, was understanding the hydrological cycle. Then in the first week uh, we had the two modules. One was runoff processes, international edition of Comet, and the other was measurement of river discharge. I know that we have a hydrological observation as one of the responsibility for all water resources department, and this measurement of river discharge is a very fundamental module for any hydrologist who want to gain knowledge and skills in hydrological observations. And there was a assignment also in the first week, and that assignment was regarding the discharge calculation. So many of you have submitted the assignment, but as rightly told by Ashiji, those are, some of them are in a draft stage. Unless you submit it finally, we will not be able to grade it. And all the assignments which have been submitted, we will be grading them. We will be giving marks to them, and we will also convey you as to whether your assignment was totally correct, partially correct, what was the issue, what could have been done to improve the results, so on and so forth. So everybody of you who have submitted that assignment, discharge calculation assignment, will receive grading as well as feedback from all of us. It may take some time, but be sure that we will be giving you that feedback for you. In week 2, we had two modules: unit hydrograph theory, and the second was stream flow routing. So these modules were of international edition level, prepared by Comet. And we had one optional module also, how to derive unit hydrograph. This module was developed by National Water Academy, and I'm sure many of you would benefit by going through this optional module as well. So optional module means even if you don't complete it, and you complete all other compulsory modules, then you will get the certificate. Okay, this is not a compulsory one. Even if you don't complete it, it won't have any effect on your certificate as such. Okay, but I'm sure all of you would like to take this module, pass the assessment, and you are also supposed to give a feedback as to how the second week was for you. Okay, so today is the last day of the second week. As I have seen the grading, many of you have completed the assignments, completed the modules, but some of you are lagging behind. Okay, so today, this particular webinar we have organized to have a direct one-to-one interaction with the participants, because what happens when you undertake the modules, you may have doubts, you may have difficulties, and getting those doubts cleared through course forum or through WhatsApp or through messages sometimes becomes a bit difficult. Though you are encouraged to send us any query on these aspects, any query on any of the aspect of the training program, including modules, technical issues, anything, and our faculty members will respond to it. But then we thought that it is much better to have a direct one-to-one interaction, to take a recap of the things that we have done up till now, and also to give you some knowledge enhancement on the respective subject, and also to clear all your doubts, have a very fruitful discussion in which not only our expert faculty, Shri Ankit Dudeja ji, will give you a presentation, but all of you are also requested to put forward your queries, your doubts, and also share your experiences in this webinar. So with these words, I will give the control back to Shri Ashit ji to take the webinar forward. Thank you.
Thank you very much, sir. Thank you for all the information you gave and encouraging the participants to take the modules. Now, with this, I request Shri Ankit ji to interact with the participants. Ankit ji, over to you. Ankit ji, your voice is not audible.
चेक द माइक्रोफोन प्लीज, आपका माइक्रोफोन ऑन है क्या?
Is it audible now?
Yeah,
Yeah,
it's
yeah.
audible.
Okay, sir. Thank you, Chaska sir. Thank you, Ashish sir, for welcoming me and giving me this opportunity to interact in this particular course program. Not very long back, maybe 10 years back in 2015, I was on the other side of this course. I took this course. From my personal experience, this is a wonderful course. Like a lot of things which are difficult to understand through pictorial representation, through animations, they have tried to simplify the things. And it's really awesome to understand through something like this, even if faculty is not available for teaching that particular topic. So with your permission, I will share the presentation.
Yeah, sure.
Yeah, Ankit,
Yeah, please.
yeah,
Just an introduction. I'm Ankit Dudeja, currently working as executive engineer in Central Water Commission, Bangalore. In initial 7-8 years of service, I have served in hydrology studies organization, and whatever experience I have gained in that 2 or 2.5 tenures, I'll be sharing in this particular lecture. What I plan to do is I'll be giving a small presentation. It'll cover whatever has been covered in the last 2 modules, the basics of it. I've even tried to incorporate some of the things of practical usability or practical applications of hydrology, which I found that something was missing. I have tried to incorporate it in this particular session. There'll be some things which I may have missed out. If at all something I missed out, you can ask me during the session. To the knowledge which I have, to the extent of knowledge I have, I'll try to answer the questions after this particular session. I'll be taking around 30 minutes to 45 minutes for making this presentation. Thereafter, it will be an open house. Open questions can be taken. Whatever I'll be able to answer it now, I'll try to answer it now itself. Whatever not, I'll assure that I'll get back to you once the things get clarified or things are clarified by me. I'll start the session. I hope the presentation is visible to all.
yes, it is visible.
Thank you. Okay, talking about water. We have huge amount of water on Earth. If we talk about the quantum of water, it's significantly huge. It's 1386 million kilometer cube of water. 1 kilometer by 1 kilometer by 1 kilometer is 1 kilometer cube. When we talk about the water on Earth, it is 1386 million kilometer cube of water, which is significantly high. But if you see in the picture, the bigger dot, the water over here, this is the total quantum of water with respect to the volume of Earth. Now, though the quantum of water is quite high, the actual usable water or actual water that can be used for our usages, it's relatively low. To quantify it, around 97% of the water is there in oceans. We don't say that it is not usable, but it is saline in nature and you need a lot of treatment for using it for any of the domestic purposes or usable purposes. Remaining water, which is around 3.5%, 1% is saline. Even though it is there on land surface, it is saline in nature in various grades like Chilka and other bodies, which is saline in nature, not readily usable, not considered as fresh water. Remaining water, which comes out with 2.5% of the overall quantum, around 35 million cubic meter, that is fresh water on the land surface. But even out of this, around 60%, more than 60% is there in solid state. Glaciers, snow caps, it's all frozen water. Again, this water is being utilized by us. This water is contributing to our perennial rivers, Ganga, Brahmaputra. We are getting water from this storage of water, but we cannot readily control it. Let's say we want water today, we cannot heat up that water and use it. So again, we have huge amount of water, 24.4 million kilometer cube. But again, it is not very like readily usable kind, cannot be controlled water. Even the remaining water, 32%, around 10.6 million kilometer cube, which is there in liquid state on the land surface in fresh condition, 10.53 million kilometer cube, that means more than like 99% of it is there inside the ground, which we call it as groundwater. Now, this surface water, which is there in liquid state, is the smaller dot over here. Out of this, the small dot that is hardly visible in this particular picture is something which is surface water that we see in as rivers, in lakes, in reservoirs. Anything that you see in the surface is that small dot, which constitute around 0.083 billion kilometer cube of surface. This is just a basic background of water. Once we are talking about hydrology, it totally revolves along hydrological cycle or water cycle. If we talk about the definition of hydrology, it is nothing but science of water, Jal Vigyan, इसको हम हिंदी में भी बोलते हैं. If we understand each and every concept of how the water is moving from one form to another, from one system to another, more or less we cover the hydrological aspects, whatever are needed. And again, this aspect is very like, it has a huge importance because for a country like ours, management of water and like managing it effectively, optimally is very essential, considering the skewed nature as well as skewed nature of rainfall, as well as the population. Before starting with it, we'll spend a few minutes on this particular this thing, water cycle. And those who have done the pre-module have covered this particular aspect. I won't be taking much time, but we'll just cover it in a short this thing. We have huge quantum of water in the oceans. Huge volume of water is available. We'll start our water cycle from there itself. When this water gains sufficient amount of energy in the form of heat, mostly provided by the sun, when sun's energy reaches the ocean surface, water molecules may get evaporated. They get some threshold of energy, which we normally call it as latent heat of evaporation or vaporization. Getting that much amount of heat, they vaporize, they get converted from liquid form to the gaseous form, the vapor form. This vapor saturates the air above the water body. This saturated air with various forces or various processes may rise up due to convective action. This saturated mass of air having good quantity of water in it may rise up in convective action, and it may move up in the atmosphere and may get supercooled. This supercooled liquids are nothing but the clouds that we see. Again, you may have some quantum of water which precipitates down from this place itself. Once it is there in the saturated form, it may get transferred to the liquid form, completing the water cycle in one sense. But we'll be stressing on those portions which are getting this water on the land surface. So this water which got evaporated, saturated the air, it moves up due to convective action, it solidifies, it supercools itself, it forms clouds. These clouds again get acted upon by a force of nature, that is wind. It transfers itself in horizontal and vertical directions. Many of the clouds precipitate over the ocean itself. Now, whatever is precipitating over the ocean itself, it is completing the water cycle. We are not very much interested in that particular portion. And there was a study long back from WMO itself, which had stated that whatever evaporation takes place from the oceans, about 91% of it gets precipitated in the oceans itself, completing the cycle in a form. Only 9% of the evaporated water from oceans come and precipitate on the land surface. Now again, whatever clouds are coming on the land surface, and when the meteorological conditions are favorable, they precipitate down. This precipitation is of importance to us because this is supplying fresh water on the land surface, which can be used for various usages for mankind and other usages. Now, whatever precipitation is coming down, it can come down in both the forms. It can come down in solid form as snow, ice, hail, it can come down as liquid form, that is liquid water. We call it as rain. Now, whatever is coming down as snow is a separate component. It is mostly there at places which are at higher altitude, sub-zero temperatures. Any water which is coming down as precipitation, as liquid water, touching the ground has three fates. After touching the ground, it can either get evaporated, going back again in the atmosphere. It can get infiltrated. It can go into the surface, maybe augment the groundwater or move as interflow or like subsurface flow towards the surface, or any water which is in excess to the infiltration moves over the surface. We call it as surface water. And this surface flow moving over the surface goes and like join some of the streams. These streams may join rivers. River may again take this water back to the oceans, completing the water cycle. Again, whatever water is there in rivers, it keeps on interacting with the groundwater. Sometimes groundwater like augments the river water, and we find like perennial rivers even during non-monsoon season. And during other times, we may even find rivers which are augmenting groundwater, which are supplying water to the ground. We call it as influent rivers, and they support groundwater. That means this interaction between ground and surface keeps on happening. And again, whatever with the interaction of ground to surface, the water is taken back to oceans, completing the water cycle. This overall is nothing but the hydrological cycle or water cycle, which we start studying from the very basics, pre-nursery classes, primary classes at least. This is overall, like this is known to everyone. But one concept which I would like to point out, which is important in terms of hydrology, is the other term which is there on the screen, that is branch cycle. Now, hydrological cycle, when we say, is under the virgin conditions of topography and meteorology. That means whatever water is coming is moving over the surface, it is going to the streams, it is going back to the oceans, without taking into consideration what all anthropogenic changes have been made to that system. Now, under the virgin conditions, under the pre-human era, when there were no structures, there was no regulation to like rivers, whatever we discussed in the water cycle was applicable. But with like intervention, with human intervention, lot has changed. We have created dams, we have created structures, we have started diverting water, we have started storing water, we have started detaining water. Now, because of all these changes, because of all these interactions, wherein we are like amending the flow which was supposed to go in the rivers, that complicates our hydrology. Now, even though our hydrological cycle concept says that some quantum of water should be available in the rivers going back to oceans, but in actuality that is not there, because water has been diverted from some or the other diversion or storage structures, and that water is not available. Now, while working out with hydrology, it is important to know both the hydrological concepts as well as the branches that have been created in that hydrology. And understanding and incorporating both simultaneously helps us like in planning, managing, and designing of water resources systems. I'll prefer doing this. I'll complete this particular session and I'll call for questions and answers. Even if whatever I'm speaking, if at all some doubts are there, we can discuss about it at the end. In hydrological cycle, we only have four components: as atmospheric water, which takes care of evaporation, precipitation, and evapotranspiration. Again, it has been covered in this module 2. Then we have surface water, in which there's some amount of losses, infiltration, percolation. We have movement of water even on the subsurface, which is adding to the quick response runoff, which is adding to the like stream flow in a short duration of time after rainfall. And we have also storages and like surface movements over the surface. Then we have groundwater interaction. We have like groundwater table. We have storages in the ground. Again, there is interaction between surface and ground, which is a function of what type of like soil is there, what type of water is there, what type of aquifer is there, what profile exists in the subsurface, etc. Then we have a contributor of like our hydrology, that is snow or ice, that is the glaciers and like the snow-capped mountains, which supply water during the warmer season, during the lean season. And again, that contributes a significant amount of water for the usability. Now, if we talk about what is the need for planning and management of water, firstly, as we said, we as a country, as India as a country, we have very skewed nature of rainfall, both in terms of spatial, both in terms of space as well as time. We have some regions in our country which have huge amount of rainfall in the tune of meters, 3.5 to 4 meters, 400 mm of rainfall. Whereas we have some regions which are having few centimeters of rainfall, and this is all annually I'm talking about. Annual rainfall varies from few centimeters to around 4 meters. And again, different type of planning, different type of management is required at places which are abundant in water to, let's say, mitigate the miseries, mitigate the disasters, and also to safeguard and supply a minimum quantum of water in places which are scarce in water. Again, planning and management is essential in that particular region. Secondly, we also have very skewed nature in terms of temporal domain. Around 80 to 90% rainfall occurs during monsoon, which is distributed from 2 to 4 months during the year. So if at all the limited quantum of water is there throughout the year, we need to plan it, we need to store water, we need to supply water during non-monsoon. Whatever water is available during monsoon, we need to store it, we need to plan it, we need to design systems, we need to plan it so that we don't become dry during lean seasons. And again, that is why the planning is required. Hydrology studies are very important because if at all we are designing any structure, if at all we are constructing any structure, any water resources structure, it is associated with huge amount of investment. And whatever investment is being made, it has to be supported by strong science, it has to be supported by a strong understanding of what we are designing and what we can expect during the life of that particular structure. So again, whatever we'll be studying in this particular DL course or in terms of hydrology, it will be mostly to understand what type of water or what type of systems will be available during the lifespan of that particular structure, and having information of what type of water will be available, how much maximum water can come, what is the minimum amount of water that is possible, how much water can be carried forward from one year to another year, so on and so forth. If this information is known to us, we'll be better equipped to plan for our future planning of hydrological cycle or water resources planning. Again, that is what is essential. If we talk about hydrology, just to give a small background of it, it normally gets covered in whatever systems are there in the DL course also. But normally there are two approaches to understand hydrology or to carry out hydrology. One is stochastic approach and one is deterministic approach. In stochastic approach, what we do is we rely on the historical data set and our understanding of statistics to answer some of our questions. Now, for planning of, let's say we are planning for management of water in the next 50 years or next 100 years. Now, first few basic questions that come to mind are, how much water is going to be available in future? What is the maximum water that can come in future? In a particular month, how much maximum water is available, or what is the average water available in a particular month? How much variation can happen in a particular month, on a particular day, or in a particular year? These are some questions which come to mind while planning any water resources system. And these questions can be answered either using historical data, that is stochastic approach, in which what we do is we collect last 30, 40 years of data set, and we say that in the last 30, 40 years, this has been shown by the catchment, this has been shown by the study area, and even in future, considering whatever trend has been shown in the past, this is expected in the future. Now, if at all we are using or we are relying on the historical data set and our understanding of statistics, and we are predicting our future, or if we are estimating our future in terms of hydrology, we call it as stochastic approach. In this, we are not bothered about how the conversion is taking place, what is actually resulting in the runoff, or what is actually resulting in the flow in the streams, how water is coming. We are not interested in that. We are just interested in getting what was there in the past. If in the past water was available and stationarity is being maintained, then in future also the water will be available. If at all some water was available in the past and you find that some trend has been shown by that, like availability of water, continuing that same trend in future, you can estimate the water availability in future using just the historical data. That type of approach, we call it as stochastic approach. Another approach that we sometimes rely on is deterministic approach, in which we don't rely on the data set, but we try to study the causative factors which result in getting that particular parameter. Let's say we want to find out what flow will be there in next 50 years. So in deterministic approach, we try to analyze how is that flow getting generated. That flow is getting generated because some amount of rainfall is coming down as rain. Some amount of snow melt is happening from the snow caps. Some amount of groundwater contribution is coming to that particular stream. So adding all the three components, we are getting the flow in the rivers. Now in future, you may have like some changes in climate, some changes in hydrology, meteorology. If at all you want to account those changes, you can modulate the precipitation, you can modulate the surface hydrology, and you can determine how much changes can be expected in future. That type of approach in which we talk about the causative factors which are causing the variation in that particular parameter. Let's say for discharge, the variation parameters are, let's say, precipitation, snow melt, waste flow contribution, the losses that are taking place. If at all we account for all these changes, all these parameters, and we assess, we forecast our hydrology, we forecast our discharge in future, that type of approach is called deterministic. Both the approaches are good enough and they are relied on various amount of times. Stochastic approach is good if at all historical data is available and it is reliable to be used. Deterministic approach is again very good approach if at all the data gets validated, if the model gets validated, this can be used. And both the approaches are very frequently used in hydrological studies by any of the hydrological organizations as well as universities. Okay, talking about the sessions that have been done, whatever has been talked about up till now, that was covered in the pre-course, if I'm not wrong. Talking about runoff and measurement. Measurement, I guess most of the people have already been associated with. They have seen the measurement of various hydrological parameters at the field. Once the information is there in terms of rainfall as well as the runoff which is there in the streams, we can use that information. We'll be using that information. We'll see how. Now, talking about runoff, again, it is very essential. Once we are planning, designing, or managing the water resources, we need to know how much water is available, forecasting and prediction of water. This water comes from surface, ground, snow melt. Again, as in the module, there are three processes of movement of water. Whatever water is coming to the surface, it can get infiltrated. It moves in the inside the ground also, it moves over the surface also. There's some amount of storages which take place. These storages can be on the surface, as in the form of lakes, ponds. It can be in the form of subsurface, as groundwater table or groundwater, or in the form of soil moisture. Whatever is getting retained, that is again storage for the whatever water has come in the system. Then the module talked about quick response runoff. Now, whenever, whatever amount of water we see in the river, we have already talked about that it has contribution from snow, it has contribution from rainfall, and it has contribution from groundwater. Now, whatever contribution is coming from ground and whatever contribution is coming from snow, more or less it is constant in nature. There is not much variation in this type of flow. But once we are talking about rain contribution, it is a quick response contribution. It rains, and whatever the rainfall occurs within the catchment, the water moves along the surface or along the subsurface and comes to the river. And normally the variation in the water level, whatever like fluctuation in water level we see in the rivers, is mostly contributed because of the quick response or because of the rainfall contribution. And again, it is an important contribution. Whatever is contributed because of a particular rainfall event, we call it as a quick response runoff because of that particular storm event. Again, the module talked about infiltration excess and saturation excess runoff. Infiltration excess runoff is nothing but whatever amount of rainfall is coming in, the rate of rainfall is greater than the rate at which percolation can take place in the soil. If the rate of rainfall is higher, even though the soil beneath is not saturated, but water will not be going inside, water will be moving over the surface. That type of surface runoff, we call it as infiltration excess runoff. Whereas there can be a time in which whatever water was moving inside the surface gets saturated, the soil gets saturated beneath, and there's no more percolation which is taking place. In that particular scenario, whatever runoff is taking place or whatever excess rainfall is coming in, it moves over the surface and we call it as saturation excess runoff. Now, whatever runoff, whatever water we see in the rivers or whatever water is coming in or getting converted from rainfall to runoff, the conversion of rainfall to runoff depends on a lot of factors. Some of the properties or how the conversion is going to take place, in what manner the precipitated water is going to come out in the rivers, is going to be a function of a lot of parameters. Some of the parameters are hydrological parameters, that is dependent on the basin properties, area of the basin, shape of the basin, slope of the basin, like alignment of the rivers, drainage density, roughness. And I'm very sure that through the animations and through the pictorial representations, these things would have been better clear to you than just reading and just me like speaking about it. There are other factors of meteorological factors also which contribute to what type of runoff will get generated. Something like what is the intensity of rainfall, for how much duration of time the rain occurred, what was the direction of the storm, whether it was moving in one direction or the opposite direction, what was the spatial extent of rainfall, whether it was like uniformly distributed, it was concentrated on one portion, or it was like multiple rain events were there within the catchments, so on and so forth. Again, the number of losses, like what type of losses will happen, will depend on what type of temperatures are there, what type of soil properties are there, temperature and humidity for the evaporation and evapotranspiration, and soil properties for the infiltration to be taken. Module also talks about rainfall runoff modeling, which is, as a hydrologist, we are interested in finding out what is going to happen in the next 50-100 years. Now, for predicting the next 50-100 years, we should have reliable data of the past, let's say 30, 40, 50 years. Sometimes for some of the catchments, we have good amount of data set. If at all we have good amount of data set, that data set can help us understand the hydrology. Based on understanding of hydrology, we can replicate our concepts to the ungauged basin, the basin which we are planning, and we can work with it. But many of the basins in our country and in the developing countries, these are not gauged. Not gauged in the sense we don't have historical data. Now, if at all we don't have historical data and we still need to plan for the future, we need to formulate some or the other mechanisms, some of the other processes to understand what can be expected in future. Now, for estimating that, one of the most crucial tool is rainfall runoff model. The tool helps us convert the rainfall to runoff. We know how much amount of rainfall is coming. This tool helps us in converting that rainfall to runoff. And this concept of converting, or this modeling concept, we call it as rainfall runoff modeling. Normally, like any other model, this has three components. One is the input, which is, in our case, it is mostly the rainfall. The next one is the process, that is, how is the conversion taking place? The rainfall, how is it getting converted to runoff? It may be a complicated model. It can be as simple model as a rational equation, or it can be like just a conversion factor, runoff factor. And output is nothing but the runoff. So if at all you're taking these three steps, Yeah, put in the input. If at all you know how the processes work, how the hydrology works, it will help you give the output. Now, these three steps, if any of the two steps are known to you, the third can be estimated. Let's say we know how the conversion takes place from rainfall to runoff. That means process is known to us, and rainfall is also known to us. In that case, using the two components, we can estimate how much amount of outflow is going to come, how much amount of runoff is going to get generated. This type of use of this model is called a forecasting model. The other way around, let's say we have input and we have output. We have rainfall also, we have concurrent runoff also. Using these two informations, we can understand how the conversion is taking place. We can develop this model, we can calibrate this model. This process is known as calibration. Normally, in a gauged catchment, when we have both information on rainfall as well as information on runoff, using the two information, that is on a gauged catchment, using concurrent information of rainfall as well as runoff, we try to understand the hydrology, how the conversion is taking place, how much amount is going down as infiltration, how much amount is going up as evaporation, how much is the interaction between your ground and surface, how much amount is getting stored or how much amount is getting diverted. Taking that much into account, or taking all the factors into account, we can understand how actually the conversion is taking place from rainfall to runoff. And again, if a gauged catchment, rainfall is available, runoff is available, we can build up the model, we can understand the model, we can calibrate the model. The other way is also possible. We know the model, we have the model with us, and some amount of runoff has been observed, and we can use it for investigating that what was the causative factor for causing that runoff. We can use the, let's say, some critical event occurred, Kerala floods, Kedarnath floods. That means output runoff is available with us. And let's say we have an understanding how the conversion of rainfall to runoff takes place. Using these two components, we can assess what type of rainfall could have caused, or what type of input response would have caused such type of catastrophe. And again, these three components, it can be a very simple model as a rational model also. You give it rainfall, you give it a conversion ratio, it will give you output. It can be a complicated model like unit hydrograph model. You give a rainfall, you give the conversion, how the conversion is taking place in the form of a unit hydrograph. It will convolute and give you the output runoff hydrograph, or it will give you the direct runoff hydrograph that is expected because of that particular rainfall event. And again, understanding this like conversion, it can be as simple as a runoff factor, it can be as complicated as a purely distributed model. And I'm sure based on the pictorial representations, lumped model, quasi-lumped model, or quasi-distributed model and distributed models are clear to at least some of you. If not, we'll talk about it. Once we're talking about models, we can have different models of different resolutions in terms of either temporal scale or in terms of spatial scale. In temporal scale, we can have models which are hourly, daily, monthly, or seasonal, or even yearly in nature. We can have like models in different scales. We can have lumped models, we can have like quasi-distributed models, or we can have distributed models. The main difference or main differentiating factors between the three is, in a lumped system, what is assumed is whatever parameter or whatever characteristics of topology or methodology we are assuming, that is assumed constant for the basin, constant for the catchment. Let's say this is the catchment. We assume that the rainfall will be uniform within this particular area. We assume that whatever the soil exists, that soil is common for the entire area. If at all we talk about land use, we say that whatever land use is there, that is common for the entire catchment. Whatever characteristics, it may have some cities, it may have some forested area, it may have some vegetation, but that is all lumped as one particular parameter. If at all we are okay to live with that one characteristics or the lumping of the parameters, we can go ahead by lumped models. These lumped models are quite easy to use. They don't take into account much complexity, easy to calibrate, easy to work with, but there are a lot of redundancies, there are a lot of fine tunes which get missed because of lumping of parameters. Another model is a quasi-distributed model, wherein we may not like to have a common parameter for the entire catchment, but we can divide the basin into sub-basins, in sub-catchments, and individual sub-catchments will assume uniform properties. Now, in this particular case, we'll be assuming that whatever rainfall is happening is uniform only within this particular sub-catchment. Whatever soil properties are there, they are uniform within this particular segment. Whatever slope of catchment is there, it is uniform in this particular sub-basin, and so on and so forth. All these sub-basins are given some of the properties which may be different from each other, but are uniform within each sub-basin. And considering this particular approach, we can again model a system. It complicates the system compared to lump model, but it tries to get the sense of more distributed or heterogeneous nature of the basin. It is a data intensive thing. You need more amount of data in a quasi-distributed model. But again, the accuracy anticipated is more. The assumptions involved are lesser. The third type of model is a distributed model, in which what we do is we divide our entire catchment into grids. We divide it into small grids, and each grid is assumed to have constant properties. That means we can assume that different grids have different properties in terms of rainfall, in terms of temperature, in terms of soil properties, in terms of land use, in terms of slope. And considering all these individual parameters for each grid, we assess how much amount of outflow is coming in. This is the most detailed form of hydrology, understanding of hydrology, wherein though you need a huge amount of data set, but if the model gets calibrated, the outflow expected is much more refined, much more genuine, much more realistic. Okay, I think this thing will be coming in future. Normally, just to give an overview how this particular RR is used. Normally, the first step is we delineate the catchment. We find out from where the runoff is getting generated. Catchment is nothing but the area of land, whatever rainfall is falling within that particular area is going to pass out from a particular point in the stream. For that particular point, the catchment, whatever area is there, that area contributes to that particular point. Again, it is easier. It is a simple process to delineate the catchment. We have special tools like GIS. We can use information available in public domain, DEMs, and delineate the catchment based on the surface information of elevation. We say that we are though I missed out in the beginning. When we talk about rainfall runoff model, the main objective is we don't have information on runoff for all the basins, but we have information on rainfall for a much longer period, and it is much better distributed. We don't have gauged rivers throughout our country. We have 1 or 2 gauges in each river. Every point of the river is not gauged, but every area of land is gauged in terms of rainfall. The rainfall network in our country is much huge, much dense compared to the runoff measuring HO stations. Secondly, even if we don't have rain gauge stations at a particular point, we have something known as satellite given rainfall. We have something like radar based, something like satellite based rainfalls, ERMM, GPM, which can give us some idea about type of rainfall which can occur, even though we don't have any observed values in that particular region. And if at all rainfall is there, and we can know that what is the process of conversion of rainfall to runoff, we can use it to estimate how much amount of discharge is coming in or how much amount of flow is going to get generated using the rainfall runoff approach. So in the steps involved, first was the catchment delineation, that is from what area the contribution is going to come to. The next one is rainfall analysis. Find out how much amount of rainfall has occurred. If at all rain gauge station is there, that amount of rainfall can be taken from IMD. If not, whatever from satellite inputs, from radar inputs, rainfall can be taken out. It can be pre-processed. It can be like averaged out for the basin. Then we also do runoff analysis for the gauged catchments while understanding the hydrology. Whatever gauged, like observed discharges are there, we need to see whether they are consistent or not. We need to see whether the discharge which is being observed, which is being like recorded, it is validated or not, it is like genuine or not. We try to analyze the runoff also, and then we convert it from one rainfall to runoff. For conversion, we can have a runoff factor, something like a rational method, CIA. You have rainfall, you multiply it with some conversion factor, that is coefficient of runoff. Using this, you can convert it to runoff. That is one of the simplest models. We can have a unit hydrograph approach, which is also called as unit catchment response function, nothing but a unit hydrograph, wherein for a unit value of rainfall, we know how much amount of runoff is going to come in. So for a varied amount of rainfall, how much runoff may get generated can be like assessed using this particular tool. We can have complicated systems also, something like artificial intelligence, artificial neural networks, genetic algorithms. Again, these are like black box models. You give them input as rainfall, they'll give you output as runoff, and they have been trained based on past historical records. Not much can be done into refining of these models, but it has been seen that they give you good results for like planning and like managing of water in future. Talking about hydrograph, hydrograph is any graph or plot of any parameter, hydrological parameter, along with time. And normally we plot either stage or discharge, so we call it as stage hydrograph or discharge hydrograph. Now, if at all at any particular point in stream, let's say I have a stream. Let's say I have a stream at any particular point. Let's say at this particular point, I start measuring how the flow is moving. Now, discharge plotted with respect to time, something like variation of discharge along with time is nothing but discharge hydrograph. Now, again, in any stream, in any river, the discharge may come because of groundwater, it may come because of snow melt, it may come because of precipitation, because of rainfall. Now, whatever input is coming in based because of base flow or because of this thing, snow melt, it is not very, it is more or less steady in nature. It is not very fluctuating. Now, whatever is happening because of rainfall, which contributes to quick response runoff, it is mostly like fluctuating the hydrograph. And that is why storm hydrograph comes into picture, which tells us that how much is the storm contribution in that particular hydrograph scenario. Important point to know is, in a particular catchment, let's say I have a catchment, something like this. If in one catchment, two different type of storm comes in, the rate at which the water comes out will be different. Similarly, if one storm comes on two different catchments, again, the amount of water that will be coming out of individual catchments will be different. That means the problem in hand is quite complicated. It's difficult to find out for an unidentified storm or for an unknown storm, how much amount of contribution will be given by that particular catchment. Again, these points have been like made clear in the presentation also. Let's say this was the rate at which the water level was initially decreasing. It can be a constant value if at all it's a stable river. Let's say some amount of rainfall occurred. Because of this rainfall, the water started rising. Even though the rainfall stopped at this particular point, there was some time for which the water was coming out, the discharge kept on increasing. After a particular time, most of the contribution passed off, the discharge started reducing again, it came down. There are some important like terminologies inside this. We have a rising limb, we have a crest segment, we have a recession limb, we have a point of inflection, which effectively tells us the most of the contribution has come out of the system, and so on and so forth. There'll be a point wherein the storm hydrograph ends, and thereafter again the base flow starts, and we call it as end of direct runoff. Again, the module talked about unit hydrograph theory, which is nothing but a unit hydrograph is nothing but a hydrograph which has been prepared or which has been generated for a unit volume of rainfall occurring uniformly within the catchment at a uniform rate in terms of like space and time for a specified duration of time. And if we know that unit value, let's say we know that for 1 centimeter of rainfall in a catchment, the hydrograph follows a particular pattern. Now, if at all the rainfall is greater than that, we can modulate that hydrograph, we can increase the hydrograph by the same ratio, and we can estimate what higher discharge can be anticipated for the like rainfall event that has come into existence. Similarly, if the rainfall is less than 1 centimeter, if it is less than the unit value, the rainfall can be modulated, or the unit hydrograph can be modulated. It can be reduced by the same fraction, and we can get the amount of discharge. Again, there are two assumptions to it. Again, it has been talked about it. We can talk about time invariance and linear response. If the rainfall is higher, by the same proportion, by the same factor, it can be increased. The unit hydrograph can be increased or decreased to get the effect of a particular rainfall event on that particular catchment. Again, the module talks about using of unit hydrograph theory, changing of duration, using the unit hydrograph for a complex rainfall hydrograph. Examples have also been given into it. Talking about application of unit hydrograph, as far as CWC is considered, design flood analysis are purely dependent on unit hydrograph analysis. And for generation of unit hydrographs, there's a entire volumes called as flood estimation report, FERs, freely available on CWC's website. For different regions, different mechanisms, different processes have been given to develop a unit hydrograph. Using these unit hydrographs, you can estimate what type of floods can come in. This is one of the applications. Extension of flood flow records, if at all flood flow is not available and you have a conversion factor, using critical values of floods which have occurred in the past, you can try in converting, or you can try in extending the records using a unit hydrograph. Again, for flood forecasting and warning systems, again, this approach can be used because a flood hydrograph or a unit hydrograph can be prepared for a very short duration also, for 15 minutes duration, half an hour duration, 1 hour duration. And once applied on a real event, on a real time basis, it gives you what type of outflow is expected, and appropriate mitigatory action and forecasting can be issued based on the forecasts. Talking about routing is nothing but to assess how much amount of flood will be obtained or will be observed at any particular point, if at all flood at any other point is. Let's say this is a stream, and at this point we know what type of flood is moving, how the stage is moving, or how the discharge is moving at this particular point. At any point on the stream, if we want to find out based on the flood available at this point, the process of assessment of flood at any other point, we call it as routing. We call it as flood routing. Normally, the flood routing is of two types. One is hydrologic routing. We also call it as lump routing, in which we put in a lot of simplifications. We put in a lot of assumptions, and we say that only continuity equation needs to be maintained. Whatever water is going inside the system has to come out of the system. With this basic assumption, and assuming that the flow is steady and uniform, we can route the flow. We can find out from one end to another end how much amount of water is going to come in. That type of approach of routing, we call it as hydrologic approach or lumped system approach. The other approach is hydraulic approach, which is quite complicated, using not only continuity equation but also momentum equation, and using the two equations simultaneously. Because it is an hyperbolic equation, it is difficult to solve it by pure mathematics. We normally have to rely on either numerical techniques or some of the other techniques for solving the equation. And normally, you must have heard about the Navier-Stokes equation. That is nothing but helps us in hydraulic routing. Yes, there's a comment. It looks like you're sharing videos or animations. What to include your computer audio while you are sharing? No, there's no audio into it, and I have not taken any animations from the DL video. Some of the images have been taken, but not the video. That video is just for animation's sake, nothing else. Okay, talking about reservoir routing, it is an important form of routing in which, let's say I have a reservoir. I know how much amount of water is coming within that system. Reservoir routing helps us understand if some amount of water is coming inside, how much amount of water is going to go out. Normally, what we use in this particular case is lumped routing or hydrologic routing. In addition to the continuity equation, in addition to inflow minus outflow is nothing but change in storage. In addition to that, one equation is used, that is storage is a function of discharge, which is quite true if at all we are taking this assumption. Because if you see in this particular figure, whatever is the amount of storage, it is nothing but the function of height of this particular water level. And whatever amount of discharge is passing out, again, that is a function of what is the height in this particular system. So in one sense, we can say that storage is a function of discharge. And using this particular scenario or using this particular equation, we can route down or we can estimate how much amount of flood will be coming out of a reservoir. That type of routing, we call it as level pool routing or hydrologic routing. We can have channel routing also. Again, in channel routing, we are interested in finding out once we are moving on the channel, along the channel, in what format the discharge is getting reduced or in what manner the discharge is getting affected or hydrograph is getting affected. One of the methods talked about in this particular DL course is Muskingum method, widely used in CWC. The same prism concept is used. We try to formulate two equations. One is a continuity equation, inflow minus outflow is nothing but the change in storage within that particular reach. And the other equation is storage is a function of both inflow as well as outflow. And inflow is a function of whatever is the starting of the wedge. Outflow is a function of what is the ending of the wedge. Taking an average of it, you can estimate how much amount of flow is passing by or how much amount of variation will happen in the flow. Using the equation of continuity, that is I minus Q is equal to S, and the equation stating that storage is a function of both inflow as well as outflow, both K and X are constants, we can estimate how much amount of changes are going to happen while movement of water from one reach to another reach. This is typical Muskingum method. There are other complicated methods also, Muskingum method, lag and route method is a very simple method in which we assume that there is no attenuation, it just moves along. There are other methods of complicating the things also. We can use Navier-Stokes equations with some assumptions. We can route the flow using this complicated equation which we talked about earlier. I think this was all in terms of what has been done in the last 2 weeks. I think we can devote some time on question and answers and whatever doubts you have or whatever you want to ask me regarding hydrology.
Yeah, thank you, Ankit. The participants are requested to ask their doubts to the faculty. Any doubts you are having, you can ask to the faculty. So I hope you are not having any doubt. You can even write in the chat box also. We are having around 50 participants and every participant is having no doubt. So everything is clear. So I hope now the quizzes will be attempted. Are we audible or not?
It's audible to me, sir.
Yeah. So no one is responding.
So we can have that. If at all some doubts are
Sir,
there,
it's
it can be
audible.
shared on
Yes, yes.
email.
Please, anyone is asking any question? Yeah.
Yes, sir. Balaji, assistant geologist from groundwater wing of Water Resource Department, Government of Tamil Nadu. I gone through 2 weeks of these modules, which are very informative and very helpful to learn the hydrology as a whole. And these models are very understandable, and so we don't have much of a doubt on this. We didn't ask. And the illustrations and the animations are more informative. That gives full knowledge without any scope for non-understanding. So this is very good, very informative. I feel very happy to attend this. So thank you. Presentation given by Ankit ji also very clear and very informative. So thank you for that's all.
Thank you, Balaji ji. This is the message for others also who have not gone through the modules. Please go through them. These are very simplified modules. You will be able to answer the quizzes, but first you have to go through them. Anyone else? Any question? Anyone having?
You can pose your questions through the chat box also. There is a chat box. If there is an issue with your microphone, you can type out your question in the chat box, please. Any questions? Good morning, Pankaja. आपने मैसेज किया है. You want to ask any questions? Either you can type it in the chat box, या otherwise you can make your microphone on and speak.
Pankaja madam, if you want to ask something.
So you are not audible to us. I think there might be some issue with your microphone. You can type the question if you would like. You are not audible to us. Pankaja madam, you are not audible. You can type the question in the chat box. In the meantime, if there is anybody else who would like to ask a question. Yes, I think Pankaja madam had said that there is some problem in the microphone. So you can type the question, no problem. But in the meantime, you have received one more question from Tamil Nadu Water Resources Department. If I used a rainfall runoff model, how much accuracy will attain in study area?
Okay, sir, I'll try to answer this. So whenever we talk about a rainfall runoff model, normally we are supposed to calibrate that model. Calibrate that model meaning you have a gauged catchment, you use the known information of rainfall and known information of runoff and develop the model. While developing the model, there's a process of using some data set for calibration and some data set for validation. Let's say I have 30 years of rainfall runoff concurrent data set, and I am developing a model for this thing for that basin. So what will happen is for 30 years, what I'll be doing is for 15 years, I'll be calibrating the model. I'll be understanding how the conversion is taking place. What all parameters are involved in conversion of rainfall to runoff. For the remaining 15 years, I'll be validating that model. Validating that model meaning I'll be applying my understanding based on the first 15 years and check whether it is working on the next 15 years or not. If the model is giving me good amount of accuracy, even in validation, it is giving me a correlation coefficient of more than 8.5, 8.9. I can say that that model is quite well calibrated. It is going to give me good amount of runoff estimate. But if at all it is not getting calibrated, there are questions. Again, questions arise because of the reliability of data used for making that particular model. So again, you cannot say that how much accuracy can be obtained. But if at all your data set based on which the model has been created is reliable, you can expect a good amount of accuracy, or you can expect a good amount of reliability for that particular amount. Have I answered the question? Tamil Nadu Water Resource Department.
Is it clear to Tamil Nadu or WRD? Okay. Yes, Madam Pankaja, as sir has mentioned, the Excel sheet is just for practice. It is not mandatory to upload it. This is from the optional module. So only quiz has to be attempted if you want to do it. But this Excel sheet is only for your practice. Is it clear? Yeah, that final writing assignment in this week, you have to give the choices. Just decide on which topic you will write to your final assignment, and give some little bit description about that. You have to choose the topic only. Is it clear? I hope it is clear. Any more question from any other participants?
I think Pankaja Madam is asking one more question. What about final writing assignment choice? Madam, we have already given 3 or 4 options regarding the topic on which you can select the assignment. Okay, so it is up to you to select the topic out of those 4 topics. Okay, as of now, you are supposed to only declare the topic on which you are supposed to going to give the final writing assignment. The writing of the assignment will be in the later week. I think it is in the 5th week. Okay, but you can now decide which topic to adopt, and then you can prepare in the meantime for 2-3 weeks on that one, and then in the last week, that is the 5th week, you can actually start writing the assignment. Okay, so we in our website we have already given you the details of the topic. If you can if you go to that final writing assignment choice link is there. If you click on that, it will be giving you the some of you have submitted the assignment topic. I think it has already been mentioned in the course. Let me check where it has been mentioned. Yeah, when you go to the link called post your final writing assignment topic, click on that link, and you will see the 4 sorry, there are three options given. You can select any one option for your writing assignment. All right, and you have to inform the writing assignment topic to us through another link, which is indicated as one sec, it is indicated as final writing assignment choice. All right, so through that one you have to inform us. Up till now 9 officers have informed us as to what their final writing assignment would be. Okay, and we request all of you to inform us maybe in the next 2-3 days. By Monday everybody should be informing us their choice.
So there's one more question by
Yeah.
Dr. Magendra Velu. So in case of absence, inadequate rain gauge station in a basin or sub-basin, what is the way to get radar-based rainfall data? I'll answer this, sir, with the permission. Sir, actually, like your question is, if at all that rain gauge data is not there in a particular basin, is that correct? So what happens is, if at all rain gauge data is not available, if at all IMD rain gauge station or any other department's rain gauge station is not existing, one can rely on satellite-based inputs, that is TRMM or GPM input, which is freely available. You can download it through data available in public domain. You can use that information for the study purposes. If not, what for Indian sub-basin, for India as a country, what IMD has done is they have created something known as grid-based rainfall data. Any basin which may or may not have rain gauge stations or which may have data of different durations, IMD has created gridded rainfall data for every grid. Data of last 80-100 years is available. Whatever information is required, that can be used or that can be taken from this particular graded data set. And this graded data set data can be downloaded through their website. So getting rainfall data is not at all a difficulty these days. You can take it out from IMD's website also. Or if at all data of satellite is required, through Earth Explorer, you can download the data of TRMM as well as GPM. I hope I have solved the query.
Dr. Magendra ji, is it clear?
Dr. Magendran, please, you can make your microphone on and speak.
Yes, sir. He responded, yes.
Okay, next question.
One is Surya Bharti ji. It's written that only topics and some few lines of description about is enough to submit. So you can choose a topic, and if it will be better if you write a few lines about it.
There is another question from Mr. Balaji. Is it possible to include one complete forecast work step by step done by CWC in the past for ease of understanding? Very good suggestion, Mr. Balaji. Actually, in the third week, we have a special module called flood forecasting case study. That is an international module developed by Comet. Okay, that module will be available to you from Monday. But as you rightly said, that is an international module, and you want CWC's forecasting method step by step. So what we can do, maybe in the next week, at the end of the next week, we can have one webinar more where we can showcase you a real case study of CWC. I think that is a really good suggestion. Okay, so in the next week we can have a webinar, but before that, please take that module of Comet, which is a flood forecasting case study. Okay, which will be available to you from Monday onwards, and maybe on next Friday or next Thursday we will have another webinar wherein a step-by-step forecasting case study will be presented to you. Okay. Any other questions? So I think we can conclude, Ashish ji.
Yes, sir. So I hope there is no more questions. So thank you very much, Ankit ji, for sparing your time and covering the topics like hydrological cycle, runoff processes, river discharge, unit hydrograph theory, and stream flow routing. I hope after this webinar, most of the participants who have not attempted the quizzes yet will be able to do it. and the doubts are cleared now. So with this, I request all of you to complete the work of week 2. Please choose your final assignment topic and post it. And it is also requested to all of you to give feedbacks to us also. There is a link for feedback submission, so that just like Mr. Balaji had given some advice for that CWC flood forecast. So we'll definitely do it as sir told. We'll try to do it in the next week, by the end of the week. So by this, I thank you all for joining the webinar.